Hello everyone, let us solve a very interesting question from the functional analysis part, and it is asked in the GATE 2023. In the question, given the L2 space, this Hilbert space L2 is given. It contains all the sequences whose entries are from the real number set such that this series is finite. Series is from the summation n from 1 to infinity xn square is finite quantity. Okay, and the standard norm L2 in the space L2 is given this one. With respect to this norm, this space is a complete inner product space, and the inner product is defined, xy inner product is defined in this way: summation n from 1 to infinity xi yi. This is the standard definition of the inner product on this space. With respect to and this norm is generated from this inner product, and with respect to this norm, it is a complete inner product space. Okay, and what is given, more thing is given, that M is a, this subspace M is defined in this way: it contains all the elements from the Hilbert space L2 such that this summation n from 1 to infinity xn upon 4n is equal to 0. Okay, then here M perp is it denotes the orthogonal complement of M, okay, in the Hilbert space L2, and the orthogonal complement of a set, if A is a set, if we calculate the orthogonal complements, then this is nothing but we collect all the elements x belongs to L2 such that x inner product A is equal to 0 for all A belongs to the set A. This is the definition of the orthogonal complement of a set. Okay, if you do not know it, please note down it. Okay, it will be used later. Then in the question what is asking, then we have to calculate the orthogonal complement of this element on the set M perp. We have to calculate, but the value of the orthogonal projection of this element over the space M perp is given this one, and here unknown thing is alpha. We have to evaluate the value of alpha. This is the main purpose on this question. Okay, so before going to calculate the projection of this vector over the M perp, but we do not know what is the space M perp. First of all, we have to calculate this space M perp. Okay, let us calculate. In the given question, M is given this one, this space M, it is the space M such that this summation is equal to 0, and this summation can be written in the inner product form. I have already told the definition of the inner product because it is the standard dot product in the infinite dimensional space L2. Okay, so we are collecting all the elements whose inner product with the beta is equal to 0, and x is defined in this space way, and beta is defined, beta we denote beta this element 1 by 4 1 by 4 square. Okay, then if we take the standard dot product, it turns out to be this series. Okay, so we and we denote the x comma beta inner product is equal to 0, means x is perpendicular to beta, so it can be written this one. So we are collecting all the elements from the L2 space so that that element is perpendicular to beta, means we are collecting all the elements which are perpendicular to beta. So this is nothing but the beta perp set. If this set this is nothing but the orthogonal complement of this set beta perp. Okay, now I will calculate the M perp, and M perp is nothing but the M is equal to this set, so M perp is equal to this set. So I simply put the value of M here. Okay, then here the double perp is coming, and there is a very standard result on the functional analysis. It says that if we take the double perp of a set, it equals with the span of a closure. Okay, double perp of A is equal to the span of a closure. So from this definition we will get this thing. But span of beta is a, here beta is, there is one element, so span of beta is a one dimensional vector space. So but we know that every finite dimensional vector space is a closed set, therefore span of beta is a closed set. So if we take the closure, so it gives the this set, same set, because closure of a closed set equal with the same set. Okay, but from the standard definition of span of beta is defined in this way. It contains the all the vectors of the form C beta, so that C is a real number. Okay, so finally we calculated the M4 space explicitly, and M4 space is nothing but a one dimensional vector space, and every one dimensional vector space can be represented by a single straight line. So in the geometry I am representing this red line M4, and it is generated by the vector beta. Okay, and I am taking this element as gamma. Okay, if I put in the vector notation form gamma, and I am taking this point as origin. Okay, then this is the vector beta, this line is generated by beta, and this point I am taking as gamma, and it represents this line. Okay, it is the gamma. Now here I will apply the trick from the class 12 dot product. Now I will calculate the projection of the vector gamma on this line beta. Okay, or the over the space M4 is the whole line, but beta is a portion of this line. Okay, so from the class 12 we know that this the orthogonal projection, perpendicular projection, this is the length 90 degree. The perpendicular orthogonal projection is nothing but the perpendicular projection of the vector gamma over the line beta is nothing but this length multiplied OP length multiplied with the unit vector beta cap, and beta cap is nothing but beta vector divided by magnitude of the beta vector. Here the magnitude is L2 norm. Okay, L2 norm is noted by 2 norm, so it is equal with this, and it is vector. Okay, so we have, and the OP length is nothing but the OP length in the sense of L2 2 norm. Okay, but we know that this OP length is equal to the from the standard class 12 we know that OP length, this length is equal with the r vector, length of the r vector cos theta. Okay, cos theta, length of r vector with multiplied with cos theta. Okay, so we will apply these analogous argument from the class 12. Then we will calculate the projection of gamma over M2. We denote its OP gamma vector. This is nothing but this length, this is OP length, and multiplied with the unit vector, because we are taking this projection in the direction of beta. It is asking in the question. Okay, and the beta cap vector is defined in this way, beta vector divided by its magnitude. Now we will calculate the inner product of these two elements, gamma vector and the beta vector. It is nothing but the dot product, and from the class 12 we know that the dot product of two elements is nothing but magnitude of the two vectors into the cos theta. And if we simplify it, it turns out to be this. This is nothing but the OP length. OP length we will find this one. Then we will put this OP length. Let me change the color. Then we will put this OP length because this is the OP length. Okay, here we will put. Then we will calculate these things. The projection of OP vector, projection of the gamma vector over the M2 space is equal with this length OP length into the unit vector. Okay, this is the unit vector, and from the definition of the unit vector, this is nothing but beta vector divided by magnitude of the beta vector. Then after simplification we will reach to this step. But the projection value is already given if and the here the beta vector is this one and the gamma vector is this one, and the projection value is already given in the question. This is equal to alpha times this series with this vector beta vector. Okay, so in the notation form we can write it, and because this summation can be written in this inner product form. Okay, now everything is clear. But because the projection value is equal with this from equation 1, but in the given question it is already given this one. Now we will simply equate these two things. Okay, equation 1 and equation 2. After equating these two things we will because here the inner product will cancel, and beta vector is a non-zero vector, it will also cancel. So it gives this value alpha equal to 1 by beta 2 norm square. Okay, beta norm of 2. But we know that from the definition of the inner product, beta norm 2 square is nothing but inner product of beta vector, inner product of beta vector, inner product of the beta vectors with the beta vector, and it turns out to be this series. And if you calculate the value of this series, it will it is equal with 1 upon 15, and our alpha value is 1 by 1 upon 15, so it gives equal to 15. So finally we calculate the value of alpha by using the small analogous argument from the class 12, projection of a vector over a line, because here our M-perp is a straight line, one dimensional vector space. I hope that you all understood it very well. Thank you everyone.